All right. In this video, we will be going over section 3.4. In this section, we will be talking about optimization. Basically, we will be talking about real-world applications of derivatives that we have learned so far. First, I want to start with this definition. Definition 3.9. X is equal to C is the location of a global maximum of a function f on an interval I if f of c is greater than or equal to f of x for all x in the interval I. Okay. What do we really mean by a global maximum? Well, let's see. So if you look at a graph like this on the interval a comma b, here is my graph. Okay. As you can see, what is the maximum value on this entire interval that the graph can attain, or the maximum y value? As you can see clearly, for all x values in this interval, the maximum y value is, this is the maximum y value that your graph can attain. There is no any other y value above this point. This is the maximum y value. So we say that if I take this point to be C1, we have a global maximum at C1. Why do we say it's a global maximum? Because at C1, we have the maximum y value in this entire interval. Okay. All the other y values, for example, if I take the y value corresponding to this x value, that y value is less than this y value. This is the highest y value that we can have for all the x values in this interval. So in that case, we say that we have a global maximum at C1. Okay, global maximum at C1. Maybe we'll write x is equal to C1. Okay. So we have the global maximum at x is equal to C1. What about the global minimum? What is the definition for global minimum? I have put down the definition for global minimum here. X is equal to C is the location of a global minimum of a function f on an interval I if f of c is less than or equal to f of x for all x in I. Okay. If we go back to this example, what would be the global minimum? What is the location of the global minimum? Well, global minimum is the minimum y value for all the x values in this entire interval. Okay, what is the minimum y value in this interval? Clearly, this is the minimum y value, right? There is no any other y value for x values in this interval which comes below this point. This is the minimum y value for all the x values in this interval. So we say that we have a global minimum at this particular x value. Let's call that x value C2. I'll call this x value C2. We have a global minimum at x is equal to C2. Global minimum at x is equal to C2. Okay, that's the idea of global maximum and global minimum. Now let's look at another example and try to find the global maximum and global minimum. Okay, what about this example? What is your global maximum for x values in this interval? This is a closed interval. Clearly, this is a closed interval because you have these shaded circles in either sides. That means we have closed endpoints for this function. Okay, what is the global maximum? Again, recall the definition. Global maximum, the location of a global maximum is a point x is equal to c such that f of c is greater than or equal to f of x for all x values in that interval. Or in other words, that is the maximum y value. That is the location of the maximum y value in that interval. As you can see, if you look at this graph, the maximum y value that you can see on the graph is this y value. So the location of that y value is b. Okay. In that case, as you can see, the global maximum occurs at x is equal to b. That is an endpoint. That means a global maximum can occur at an endpoint as well. Not only in the middle, like in this case, the global maximum occurred at an interior point C1, but in this case, the global maximum occurs at an endpoint. Okay, so let's write it. global maximum occurs at x is equal to b. What about the global minimum in this case? Clearly, the global minimum is this y value. Notice that this y value is on the graph. Okay, this point is on the graph. And as you can see, this is the lowest y value or the minimum y value that you can get on this graph, on this piece of graph. That means the location of the global minimum is at x is equal to a. Or in other words, we say that at x is equal to a, we have a global minimum. That is the minimum y value for all the x values in this interval. Okay, so let's try it. Global minimum occurs at x is equal to a in this case. As you can see, in this case, the global minimum occurs at an endpoint. See, this is the endpoint, right? This is the left endpoint, of course. Your global minimum occurs at the left endpoint. Here, the global maximum occurs at the right endpoint. Okay, that means the global extrema. Global extrema means global maximum or global minimum can occur at endpoints. And also they can occur at some interior points. Here is an example where you have the global maximum at an interior point, and also you have the global minimum at an interior point. Okay, what about this example? What is the global maximum? What is the global minimum? As you can see here, we have open endpoints in this case. At this endpoint, your function is not defined. That's why you have this open circle. Here also your function is not defined. What is the global maximum and global minimum in this case? As you can see here, you don't have a global maximum. If you want a global maximum, the only potential candidate is B. The location of the global maximum is B because this is the kind of a highest y value, right? But that y value, you don't have a y value because your function is not defined at x is equal to B. Okay, so in this case, no global maximum. There is no global maximum. Okay, as you can see from the graph, if you are going to have a global maximum, the potential candidate is x is equal to B. The location is x is equal to B, but x is equal to B is not in the domain of your function. So in this case, no global maximum. What about the global minimum? Do we have a global minimum in this case? No global minimum as well. As you can see, if you look at the graph, this is the minimum y value that you would expect, but at x is equal to a, your function is not defined. There is no function value at this point. So you don't have a global minimum as well. No global minimum. Okay. All right. So that's the idea of global minimum and global maximum. Okay. These are called global extremas. Global extremas means global minimum or global maximum. All right. Let's move on. Next question is, how do you find global extremas? Well, you have to do a couple of things. Notice that global extremas can occur at interior points. Okay, to find those points, you need to find critical points of the function. And they can also occur at closed endpoints. Okay, that means to find global extremas, what we need to do is you need to compare these values. What are those values? Values f of c for each interior local extremum c is equal to c in I. Okay. At each interior local extremum, you need to check the value f of c, and then you need to check the values f of c at any closed endpoint x is equal to c. And then if you have any open endpoints, you need to find the limit of the function at those open endpoints. Okay, that way you can determine whether you are going to have global extremas or not. All right, to understand this idea, let's work on an example. Yeah, first of all, before we go to the example, let me give you an overview of what we will be doing in the optimization section. Okay, here is the overview of what we'll be doing. So basically, we are given a word problem, which is in English. And then what we do is, using the data given in this word problem, we translate that problem into a mathematical problem. That means you come up with a bunch of equations. Okay, and then you deal with those equations. And then you solve that mathematical problem to get a mathematical answer. Okay, at the end of the day, not at the end of the day, you get a mathematical answer, and then you need to translate back that mathematical answer in real world terms. That means you have to write down your answer in English so that a non-mathematician can understand what you mean. Okay, that's the idea of this optimization problem. That's the overview of an optimization problem. All right, before we go to a real world application, I want to do some warm-up problem. Let's work on this problem. This example, find the global maximum and minimum values, if any, of the function f of x is equal to 2x cubed minus 15x squared plus 24x plus 20 on the interval 0, 6. Notice that we have open endpoints in this case. These points are not included. 0 and 6 are not included. So we have open endpoints. Okay. If you recall back, to compute global extrema, we need to find values of f of c for each interior local extremum c in I, and values f of c at any closed endpoint x is equal to c, and the limit of the function at any open endpoints x is equal to c. In this case, of course, we have open endpoints, so we have to find the limit. Before we find the limit, let's find any interior local extrema. To find local extrema, you find critical points. Local extrema, find critical points. Because we know that local extrema are critical points. Okay, so let's find critical points. So you set your derivative to 0 to find critical points. First of all, let's find the derivative. F prime of x is equal to 6x squared minus 30x plus 24. And this is a quadratic expression. If you factorize that quadratic expression, this is what you get. 6 times x minus 1 times x minus 4. Now, to find critical points, I'm setting my f prime of x to 0. To set 6 times x minus 1 times x minus 4 is equal to 0. Okay, notice that in this case, to find critical points, you can set the derivative to 0 because the derivative is defined everywhere. As you can see, this is a polynomial. This is defined everywhere. So to find critical points, you just set that to 0. Okay, if you set this to 0, you get x is equal to 1 and x is equal to 4. These are the critical points. Okay. Now what do? We need to determine whether we have a local maximum or local minimum we have at x is equal to 1. Okay. How do you determine whether we have a local maximum or a local minimum at this point? Well, we can use the second derivative test, right? We find the second derivative of the function. The second derivative, f double prime of x is equal to 12x minus 30. And then I'm going to plug in these numbers in f double prime, x is equal to 1 and x is equal to 4. If I plug in x is equal to 1 in my f double prime, you get f double prime of 1 is equal to 12 times 1 minus 30, which is minus 18. And if I plug in x is equal to 4 in my f double prime, you get 18. Okay. So as you can see here, this is negative and this is positive. Now, what does the second derivative test tell you? It tells you that you have a local maximum at this point. You have a local maximum at x is equal to 1. Local maximum at x is equal to 1 because f double prime is negative at x is equal to 1. That means you have a local maximum. Here you have a local minimum because your f double prime is positive at x is equal to 4. Local minimum at x is equal to 4. Now let's find those local extrema. Okay, we have a local maximum at this point. Let's find that local maximum. To find that local maximum at x is equal to 1, we have to plug in x is equal to 1 in my function. Okay, so my local maximum would be, maybe I will write it, local maximum equals f of 1. So if you plug in 1 in your function, your f of 1 would be 31. You just plug in x is equal to 1 in your function. And then here, to find the local minimum, you plug in x is equal to 4 in your function. Local minimum is equal to f of 4, which is 4. If you plug in x is equal to 4 in your function, you will get 4. That means the local minimum is 4. So we found those local extrema along with the locations. The location of the local maximum is x is equal to 1 and the local maximum value is 31. The location of the local minimum is x is equal to 4. The local minimum value is 4. Okay, we need to remember we are supposed to find the global maximum and global minimum. So we found our local extrema. That's good. Okay, what else do we need? We need to find the limit value at any open endpoints. We of course have two open endpoints, 0 and 6. So we need to find the limit values at each of those points. So let's find the limit value. I need limit as x approaches to 0, f of x. I also need limit as x approaches to 0, not x approaches to 0, x approaches to 6, f of x. What are these values? If you find the limit, you will get, by the way, here as x approaches to 0 from the positive side, here as x approaches to 6 from the negative side. Why is it positive side? Why would you put positive here? Notice that we are on this interval, so you can talk about only x approaching to 0 from the right hand side. That means positive side. Okay, to the left of 0, we are not concerned. Here you can talk about as x approaches to c from the left hand side. That's why you put a negative sign here. And to find that limit, you plug in x is equal to 0 in this function, then you will get 20. If you plug in x is equal to 0 to find that limit in this function, you will get 20. It's clear. And then to find this left limit as x approaches to 6 from the left hand side f of x, you plug in x is equal to 6 in this function. Okay, if you plug in x is equal to 6 in the function, you will get 56. Okay, now what you do is you compare all these values. Okay, basically we have these values. Okay, to find the global maximum, you compare all these values. 31, 4. You don't really have to compare this 4 because it's a local minimum. So you compare all these values. As you can see, the global maximum looks like this one. This is the highest value if you compare all these 4 values. This value, this value, this value, and this value. This is the highest value. But this is an open endpoint. X is equal to 6 is an open endpoint. That means your function is not defined at x is equal to 6. That limit gives you the highest value of these 4 values. This is the highest value, right? If you compare these 4 values, This is the highest value, but this point is not in the domain of f of x. So that means in this case, we don't have a global maximum. There is no global maximum. Okay, it is clear that we don't have a global maximum in this case because this limit value is the biggest of those four values. What about the global minimum? Do we have a global minimum in this case? Again, we compare these four values and find the minimum value. The minimum value is clearly this value, right? And that minimum value occurs at an interior point. X is equal to 4 is inside this interval 0, 6. So that means we have a global minimum in this case because this is the smallest number and it occurs at x is equal to 4. So we have a global minimum value of 4 at x is equal to 4. So we write global minimum of 4 occurs at x is equal to 4. Notice that the both values are 4 because y value is 4, your x value is also 4. That means the minimum value is 4. The location of the minimum is x is equal to 4. All right, that completes that example. This is an example where you don't have a global maximum, but you have a global minimum. All right, now let's look at some real world applications, real world problems. Okay. Okay, here is the first example that I want to go over. All right, let's go over this example. Farmer Joe wants to build a rectangular chicken pen for his chickens. He wants to build the pen so that it has the largest area possible. And he has only 100 feet of chicken wire fencing. Okay, what is the dimension? What dimensions should he use for the pen? Okay, so basically this farmer has a certain amount of fencing, namely 10 feet of fencing. Using that 10 feet of fencing, what is the largest rectangular area we can enclose? That's the question. Okay, how do you find the dimension of the rectangle that would include the largest possible area? Dimension means if your rectangular chicken pen is this one, dimension means the width and the length. Okay, I'll take my width to be x and the length to be y. Okay, how do you find x and y so that this area is maximized? That's a very practical question. You always want to maximize the area so that you can put a lot of chicken in it. Okay. All right. How do we start this way? First of all, notice that this is the amount of fencing that we have. To maximize the area, we need to use this whole amount of fencing. Okay. So how do we write an equation relating these quantities to 100? Clearly, 100 should be equal to the perimeter of this rectangle, right? The perimeter of the rectangle is 2x plus 2y. That should be equal to 100 because you are going to use the total amount of fencing given to you. The whole amount of fencing given to you. All right, now what do you want to maximize? First of all, I'll do some simplification here. I'll divide this equation, entire equation by 2. Then you get x plus y is equal to 50. Okay. Now, what is my goal? I want to maximize the area of this rectangular region, right? First of all, let me write an equation for my area. My area is area of this rectangular chicken pen is x times y. Okay. Now, what's the problem here? I have found the area. I need to maximize this area. But the problem is I have two variables here. Okay. In an optimization problem, if you have two variables, the first thing that you need to do is you need to come up with a one variable thing. You need to find your area in terms of a single variable. Of course, we can do that here because of this equation. Okay, this equation tells you that x plus y is equal to 50. I can easily isolate y from this equation. What I'm going to do is I'm going to isolate y from this equation. That will give you 50 minus x. You move your x to the other side. You move this x to the other side. Okay. Now I can replace this y by 50 minus x because they are equal. So let me replace this y by 50 minus x. Now, as you can see, this is a function purely in terms of a single variable, which is x. That's what I want. Now I can optimize this problem. I can find the maximum area by treating this as a function of x. Okay. If you simplify this a little bit more, you will get 50x minus x squared. Okay. Now the next thing that we need to figure out is what is the domain of domain that we should use to maximize this area. Domain means in what x value range are we going to maximize this function? Well, to figure that out, notice that x is the width of your rectangular chicken pen. That means x has to be greater than or equal to 0, right? If it is the length, it has to be greater than or equal to 0. And also, you know that your y is the length of the rectangular region. That means y also has to be greater than or equal to 0. So from this equation, I can argue that my y also should be greater than or equal to 0. What does that mean? Y should be greater than or equal to 0 means 50 minus x should be greater than or equal to 0. That means your x has to be less than or equal to 50. So now I have the range on which I maximize my area function. My x has to be greater than or equal to 0 and it has to be less than or equal to 50. So at the end of the day, here is my goal. Maximize AX. I'll call my area AX. Okay, this is AX. I'll take this to be AX. Maximize AX on the interval 0, 50, closed interval, by the way. Why am I maximizing my a of x in this closed interval? Because I know that my x is greater than or equal to 0 and my x is less than or equal to 50. That means the area of the region of interval of maximization is 0, 50. Okay. On this interval of x values, I'm going to maximize my area function. So I have a purely a mathematical problem now. I want to maximize this function for x values in this interval. So how do you do that? First, you find the critical points, right? Let's find the critical points. All right, let's find the critical points. I'm going to find a prime of x to find my critical points. If you find a prime of x, that would be 50 minus 2x, the derivative of your area function, a of x, okay? That is 50 minus 2x. To find critical points, I'm going to set to find critical points. I'm going to set a prime of x to 0. That means 50 minus 2x is equal to 0. That will give you x is equal to 25. Okay, so you have a critical point at x is equal to 25. Now let's determine whether we are going to have a local maximum or local minimum at x is equal to 25. Okay, for that I'm going to find the second derivative of my function, my area function. The second derivative would be a double prime x is equal to minus 2. Okay, that is already negative. That's the minus constant. You don't really have to plug in this x is equal to 25 here. Even if you plug in it here, you get negative 2. Let's, for the sake of completeness, let's plug in x is equal to 25 in the second derivative function. That will be minus 2, which is less than 0. What does that tell you? That means you are going to have a local maximum at x is equal to A has a local maximum at x is equal to 25. Okay. Now, what do we have to do? Is this going to be your global maximum? Are you going to have a global maximum at x is equal to 25? Well, we don't know yet. Let's find the function value, the value of the area at x is equal to 25. Let's find A25. A25. If you plug in A25 in your area function, you will get 625. What else do we have to do to find the global maximum? We need to make sure that that's a global maximum. Okay, we are looking for global maximums for x values in this interval 0 to 50. Okay, these are closed endpoints. So we need to find the value of the area function at these closed endpoints as well. Then only you can make a comparison. So let's find A of 0 and A of 25. They both are going to be equal to 0. If you compute that, you will see that they both are going to be equal to 0. Now, actually, let me write them as separate things. This is 0, A50. That's also going to be 0. Okay. Now you compare these values to find where you have the global maximum. As you can see, if you compare these values, the global maximum value is 625, and that occurs when x is equal to 25. Notice that 25, x is equal to 25, is in this interval, inside this interval. That is an interior point. That means you have a global maximum at x is equal to, A has a global maximum. Global maximum at x is equal to 25. Okay, now we know that we have a global maximum at x is equal to 25. But go back and look at the question. What does the question ask? We need to find the dimensions that we should use to maximize the area, right? We know that the area is maximized when x is equal to 25. So we found the value of x. Dimensions means we need to find the value of x and y both. Okay, so how do you find the value of y now? We have the value of x. The value of y is clear. We know that y is 50 minus x. So we can plug in the value of x there. 50 minus x is 25. That is 25. That means the dimensions that we should use to maximize the area would be x is equal to 25 and y is equal to 25. Okay, what does that tell you? That means this has to be a square, not a rectangle actually. A square is a special type of rectangle, right? The length and the width, they are equal. So the dimensions are x is equal to 25 and y is equal to 25. Or you could write the length is 25 and the width is 25, which is of course a square. All right, that completes that example. Let's move on to the next example. All right, here is the next example that I want to go over. Let's read the example first. You work for a company that makes jewelry boxes. Your boss tells you that each jewelry box must have a square base and an open top, and that you can spend $3.75 on the materials for each box. The people in the production tell you that the material for the sides of the box cost 2 cents per square inch. Okay, the price per unit area is given for the sides of the box, while the reinforced material for the base of the box cost 5 cents per square inch. Okay, again, the unit price is given here, okay, per area. What is the largest volume jewelry box that you can make and still stay within the budget? Okay, so that means you need to use this much of dollars, and you need to make sure that your box has the largest area possible with these restrictions. Okay, the restriction is that the cost for sides is 2 cents per square inch, and cost for the material in the bottom is 5 cents per square inch. How do you solve this problem? How do you find the largest volume that you can have for this box? Clearly, our goal is to maximize. Let me write goal to maximize the volume. Maximize, I'll call the volume V. V is equal to x squared times y. Clearly, V is equal to x squared times y, right? The volume of this box would be the area of the bottom, which is x squared times the height, or the length times the width times the height. That is the volume. I want to maximize this. Again, the problem is that I have two variables. Now I need to find a way to get rid of one variable. Remember, we did the same thing in the previous case. We had two variables in our objective function. This is sometimes called the objective function, okay? The function that you want to maximize or minimize. This is called the objective function. In the objective function, you had two variables in the previous problem. Somehow, we managed to get that function in terms of one variable. That's what we are going to do here. You need to come up with a one variable function here as well, okay? So how do you do that? That's where this data is going to help you. The cost for the sides is given and the cost for the bottom is given. By the way, we need to convert this cost into dollars, okay? Because this total amount available for you is given in dollars. So this is 2 cents means $0.02, okay? This is actually $0.02. And the other one is $0.05. This is $0.05. Okay, now let's write an equation for the cost of making the sides and the bottom. What is the cost of making the sides? You have four sides, right? This side, front side, this side, and this side. What is the cost for those four sides? Well, you need to find the area of a one side, right? The area of a one side is x times y. This area is x times y, and all the other areas are x times y, right? I mean, the areas of sides, because this is x, this is y. So we have altogether the total area for the sides would be 4 times xy. Would you agree with me? That is the total area for the sides. This side, and then of course you have this side, and finally this side. This is the total area of sides, and then you need to multiply that by the unit price. Price per area. The price per unit area is $0.02. So I'm going to multiply this area by $0.02 to find the total cost for my sides. This is multiplied by 0.02. And then plus, I need to add the cost for the bottom. What is the cost for the bottom? First of all, the area of the bottom is x squared. I need to multiply x squared by the unit price per unit area. The price per unit area is $0.05. You have this much area. Price per unit area is $0.05. So you need to multiply this area by the unit price, which is 0.05. By the way, I will omit the dollar symbol and let's put the symbol later. So this should be equal, this whole thing should be equal to, let me move this a little bit. this whole thing should be equal to 3.75. That's the money available for you. Okay. So you are using the available money to make sure that you make the largest possible box with the largest volume. Okay. So we have this relationship. From this relationship, now I'm going to find my y in terms of x. That's what I'm going to do now. Okay, so what I'm going to do is I can, of course, multiply these two numbers, 4 times 0.02, which is 0.08. And then I move this term to the other side. And then you divide both sides by 0.08x to isolate y. Okay, if you isolate y, this is what you are going to get. Okay, so we have y in terms of x. Now what I can do is I can plug in this y value here in my volume formula. Remember, my goal is to maximize the volume. Okay. All right, let me do that. All right, my a, I'll call it a of x because that's going to be, pardon me, it's not a. This time it's v, the volume. Okay, v of x. My v of x is equal to x squared times the y value. The y value is 3.75 minus 0.05x squared divided by 0.08x. As you can see, one of the x's will be cancelled here. So your answer would be x times 3.75 minus 0.05x squared. That's it. If you want, you can distribute this x. 3.75x minus 0.05 x to the power 3. Oh, don't forget your 0.08 in the bottom, okay? All right, now I have a nice objective function. Notice that I have only one variable in this objective function, which is x. Okay. Now the next question is, what is the interval of maximization? For what x values are you going to maximize this? Clearly, notice that your x is the length of a one side in the bottom. That means x has to be greater than or equal to 0. That's clear. And then notice that we have y as the height. Y also should be greater than or equal to 0, right? That's how you get this interval of maximization. Okay. So you argue with these variables, associated variables. This variable has to be greater than or equal to 0. That will give you a lower bound for your x. X has to be greater than or equal to 0. To get an upper bound, you use the other variable, y. Y also should be greater than or equal to 0. Okay. That means, what is your y, first of all? This is your y. This has to be greater than or equal to 0. That means 3.75 minus 0.05. Maybe I'll write it in the next line. This quantity has to be greater than 0. 3.75 minus 0.05 x squared over 0.08x should be greater than or equal to 0. Notice that this is greater than or equal to 0. So that means you need to make sure that this part is greater than or equal to 0. Okay, so you should have the top greater than or equal to 0. 3.75 minus 0.05 x squared should be greater than or equal to 0. If you move your negative terms to the other side, you get 3.75 should be greater than or equal to 0.05 times x squared. That will give you x squared should be less than or equal to 3.75 divided by 0.05. All right. So you need to have x squared less than or equal to this quantity. Of course, if you calculate this quantity, which is 75, So x squared has to be less than or equal to 75. Now you take the square root of both sides, assuming that this x is positive, because if x is greater than or equal to 0. Then we preserve this inequality sign, because if this is positive quantity, quantity greater than or equal to 0, we can take the square root of both sides. So x has to be less than or equal to square root of 75. That means that gives me an upper bound. X should be less than or equal to square root of 75. And already I know that x is greater than or equal to 0. That means my interval of maximization would be 0, square root of 75. Closed intervals, by the way. So my goal is to maximize v of x on 0, square root of 75. I know that interval now, interval of maximization. Let's do it. How do you maximize this? To maximize this, first of all, I'm going to find my critical points. Okay, if you find v prime of x, that will be 46.875. Of course, you take the derivative of your v of x minus 3 times 0.625 times x squared. Okay. All right. Now to find critical points, we set v prime of x to 0. Okay. If you set that to 0, you get 46.875 minus 3 times 0.625 x squared is equal to 0. From this, you can easily find that x is equal to plus or minus 5. Okay, all what you do is you send this term to the other side and divide both sides by this expression to find your x squared, and then take the square root. That will give you x is equal to plus or minus 5. But minus 5 is out of the question. Minus 5 is not in this interval. We are interested in x values in this interval. So our x value we are interested in is x is equal to 5. Okay, x is equal to minus 5 is not in the interval we are interested in. Not in 0, square root of 75. So we are not going to deal with that. This is the number that we are interested in. Clearly, x is equal to 5 is inside this interval. The square root of 75 is a number which is bigger than 8. So this 5 should be in the interior of this interval. Now let me find the value of the volume at x is equal to 5. V of 5. To find V of 5, you need to plug in x is equal to 5 in your volume function. That will give you 156.25. Okay, so that is next thing. What we need to do is we need to determine whether we have a global maximum or global minimum at this point. Okay, for that, actually, let's get rid of this one. Let's first determine whether we have a global maximum or global minimum at this point. For that, I'm going to find v double prime of x. V double prime of x would be minus 3 times 0.625 times 2x. Okay, my x value is 5. I can plug in 5 here to determine whether I have global maximum or global minimum, local maximum or local minimum at x is equal to 5. If you plug in x is equal to 5, this will be clearly a negative number. 0.625 times 2 times 5. Okay, so this is a negative number. That means I'm going to have a local maximum. Local maximum at x is equal to 5. maybe we write V has a local maximum at x is equal to 5. Now let's find the local maximum value. Local maximum value would be the function value at x is equal to 5, v of 5. That is, v of 5 is going to be 156.5. That is the value of the local maximum. All right, we have the value of the local maximum. We are not done yet. Remember, we need to analyze these closed endpoints. So we need to compute v of 0. V of 0 is clearly 0. If you plug in 0 in your function v, you get 0. And of course, if you plug in v of square root of 75, that will also give you 0. Now you are ready to determine your global maximum. As you can see, you compare these values, the values at closed endpoints. You have y value 0, 0, and then we have a global maximum value, that is 156.5. As you can see, by comparing these three values, we see that this is the highest value that you can get. Okay, so you have a global maximum at x is equal to 5. Global maximum occurs at x is equal to 5. The global maximum value is v of 5. The global maximum value is 156.5. That is the largest volume possible for your box. Okay, because v is the volume, right? So the global maximum of the v occurs at x is equal to 5. That means the maximum value of your volume is 156.5. That's what we are asked to find. If you go back to the problem, what is the largest volume jewelry box that you can make and still stay within the budget? Okay, so the largest volume jewelry box is 156.5 cubic inches. Okay, the dimensions are given in inches, so it should be cubic inches. Largest the largest jewelry box has volume 156.5. That's what we are asked to find. Okay, that completes that example. Let's move on to our last example. Okay, let's go over this example. Suppose you want to make a cylindrical can to fill 355 cubic centimeter of soda. How can you make the cylindrical can so that the area of the can is minimized? Okay, if you are running a company which produces soda cans, it is very important that you minimize the area of the soda can, but still keeping the volume that you want. Okay, why is it important? Because that will save a lot of material, right? That means that will cut down cost for you. So how do you minimize the area of the can so that the volume of the can is fixed at this number? First of all, a picture would help us to understand what's going on. Let's take the height of the cylinder to be cylindrical can to be h and the radius of the can to be r. Okay, then can we write a formula for the area? That's what we want to maximize, right? Minimize, pardon me. What is a formula for the area? That's not difficult. A is equal to 2 pi r squared. That means you have the bottom and the top. The areas of these two would be 2 pi r squared, because one of them would be pi r squared. So you have 2 pi r squared, and then you have to take the area of this side surface, that is 2 pi r h. Okay, the area of this side surface is 2 pi r h. Okay, so now we have a formula for the area, but the problem here again and again is that we have two variables r and h. That's the trouble here. We need to find a way to come up with a one variable thing here. Okay, so how do you do a one variable here? How do you come up with a one variable equation for a? Well, what we can do is we can use the given data. The given data tells us that the volume of the can should be 355 cubic centimeters. So let's argue along that. So the volume V is equal to the volume of a cylinder is pi r squared h. That's the formula that you need to know. Okay, volume of a cylinder is pi r squared h. Let me write it here. Volume of a cylinder. Pi r squared h. But in this case, we are given the value of V. The value of V is 355 is equal to pi r squared h. From this, I can find the value of h. I'm going to isolate the value of h. Value of h would be 355 divided by pi r squared. All right. Now, why did I isolate my h? Because I want my volume function in terms of a, area function in terms of a single variable. I have both r and h in this equation. So now I can replace my h by what I found here. That is purely in terms of r. I can put this quantity here to come up with an equation which has only r. Okay, so my area function, new area function, I'll write that as AR, A of R, because it's going to be a function of R, 2 pi R squared plus 2 pi R times my H. My H is 355 divided by pi R squared. As you can see, pi will be cancelled. One of the R's will be gone. If you simplify this, you will get 2 pi r squared plus 710 divided by r. Now at least I have a function to work with now. This is, by the way, yeah, so this is the area function. Okay, we have the area purely as a function of r, only one variable there. These are constant, 2 pi, 710, the others are constant. Okay, all right. Now I want to minimize my area function. I want to minimize this function. But the next question is, for what values of r am I going to minimize my function? What is the interval of minimization? That's the next thing we need to figure out, right? Clearly, r has to be greater than or equal to 0, right? Because r cannot be negative. R is the radius. It has to be greater than or equal to 0. And also we know that h has to be greater than or equal to 0. H is the height of the cylinder. H is greater than or equal to 0 means this quantity is greater than or equal to 0. Right? If this is greater than, this quantity is greater than or equal to 0, r is greater than or equal to 0, that means r can be anything here. When you say h is greater than or equal to 0, r can be anything between 0 and infinity. So an upper bound for r would be r is less than infinity. Okay, so now we have an interval for the maximization. So the interval would be 0, infinity. I'm going to minimize the area in this interval. By the way, here there's a small typo. Here it should be r greater than 0. Okay, because you cannot have, even though r should be a non-negative number, you have to have r greater than 0, because in this, if you look at this objective function, you have r in the bottom, right? So we cannot let r be 0. R has to be greater than or equal to 0. Even if you look at here, r is in the bottom, so r cannot be 0. So we want r to be greater than 0 and r to be less than infinity, because h can be anything. Okay, h can be anything, so r can be any positive number. So the interval of minimization would be 0, infinity. This is the interval of minimization. All right, now let me write my problem again. So here is what I want now. Okay, here is my mathematical problem. I want to minimize the area A of R given by this function on the interval 0, infinity. Okay, 0 is excluded. This is an open endpoint. Okay. All right, now to minimize this, what do? We find critical points of AR. A prime of R, you take the derivative of the area function with respect to R, then you will get 4 pi R minus 710 over R squared. That's the derivative. And to find critical points, you set critical points. You set A prime of R to 0. If you set A prime of R to 0, 4 pi R minus 710 over R squared will be 0. And now if you find your R, if you solve for R, you will get, first of all, you will get R cube is equal to 710 divided by 4 pi. And of course, now you can find your R. You take the third root of this number. 710 divided by 4 pi. You take the third root of that number. That is the value of R. All right, now we need to determine whether we are going to have a local maximum or local minimum at this point. Okay, so for that, I'm going to find the second derivative of my area function. A double prime R is equal to 4 pi minus, it should be plus actually, okay, this is the second derivative of the area function. Now, to determine whether I'm going to have a local maximum or local minimum at this point, I'm going to have to plug in this number for my R in the second derivative function. A double prime, I'm plugging that number R, 710 over 4 pi to the power 1/3 is equal to 4 pi plus 710 times 2 divided by R cube. R cube is nothing but this number. 710 divided by 4 pi. Clearly, as you can see, this number is positive. That means by the second derivative test, A has a minimum, local minimum. Minimum at R is equal to 710 over 4 pi to the power 1/3. Okay. All right. Next, what I'm going to do is I'm going to find the function value at that point. Okay. So let me find A of to find the local minimum value. Okay. 710 divided by 4 pi to the power 1/3. I'm going to find this value. Okay, this is the local minimum value. I know that I'm going to have a local minimum at x is r is equal to this number. So I plug in that value of r in my area function to find the local minimum. In fact, my local minimum value is this number. Clearly, this number is some positive number, some positive real number. Okay, we are not done yet because we have two open endpoints. That means we need to find the limit as x approaches to 0 from the right hand side and the limit as x approaches to infinity. Let's find those to finish this up. Okay, what would be this limit? Limit r approaches to 0 plus ar. What is that limit? As you can see, if you look at this function, as r approaches to 0, this will be 0. But as r approaches to 0 from the right hand side, this would look like 710 over 0 plus, which is plus infinity. So this limit would be plus infinity. You can also see that this limit is clearly infinity again. Now, to find the global minimum, you have to compare these three numbers. Remember, finding the global minimum of this function on this interval was my focus. Okay. To find the global minimum, I'm going to have to compare these three numbers, these two number and this number. Which one is the minimum? Which one is the least number? Clearly, this one is the least number, right? Because this is a nice positive number. These two are infinity. So the global minimum of A of r occurs at r is equal to 710 divided by 4 pi to the power 103. And what is the global minimum value? Value is equal to whatever the value we obtain here. This is the global minimum value. Let me copy the whole thing. This value. So the question asks, how can we make the can so that the area is minimized? So we have to make the can so that your radius of the cylinder is this much. The value of the radius is this, and the value of the height. How do you find the value of the height once you know the value of the radius? So what you do is I can use this equation. I know that h is equal to 355 divided by pi r square. Okay. So I'm going to copy it over here. So here is my h. I'll copy this to the bottom. This is the value of h. So the value of h would be 355 divided by pi times r squared. R is 710 divided by 4 pi to the power 1/3 whole thing to the power 2. Okay, that will be the value of h. So again, you have to make the can so that your radius has this value and the height has this value. Okay. All right. With that, we conclude that section, and I'll see you next time.